nuclear physics and nuclear chemistry. This is one of my favorite topics. As I look back, if I were to go into a particular field of science instead of becoming an educator, I might have chosen nuclear physics or astrophysics. These subjects have always fascinated me. Nuclear physics also gets kind of a bad rap, I think, because of the fact that since you're studying the nucleus of an atom, which is very difficult to do, and it's not something that's easy for many people to envision, and because of the fact that most people have no background at all in nuclear chemistry or physics, because it's usually a unit that they never get to in their science class, there's an awful lot of misperceptions, misconceptions, mysteriousness to this subject. And I think it explains a little bit why there is a healthy skepticism, maybe one that's not totally deserved, as far as nuclear energy is concerned. But we'll get more into that much later in this unit. This is the last main unit that we're going to have a chance to go into any depth on in our college physics class. Now, you might remember from chemistry, we've got a weird use of capital letters in the English alphabet to stand for fundamental terms. The atomic number, which is going to be a whole number, 1, 2, 3, 4, 5, which represents the number of protons in the nucleus. That whole number is represented by the letter Z. Seems strange. The neutron number, this one at least makes sense. I'm going to use a capital letter N for that. Remember, N it typically means the number of something, like the number of turns of wire in a solenoid. And then the mass number is going to be represented by the letter A. And the mass number is not the same thing as the weighted average or the mass average. It's not that number on the periodic table. That is not a whole number. The mass number is a whole number because it refers to the number of nucleons. In case you forget what that word means, a nucleon refers to the particles in the nucleus. So the number of nucleons would be the number of neutrons plus protons, because those are what make up the nucleus. And you'll hear that word nucleon used a lot more in nuclear physics than you would have in chemistry. Another term from chemistry that you've got to remember is the term isotope. Iso, of course, is the prefix which means the same. And so we're talking about different forms of an element that have the same number of protons, but they have a different number of neutrons. So because they have the same number of protons, their chemical properties are the same. How they interact, how they combine, and what proportions with other elements is the same regardless of the isotope. But their mass numbers would be different because they would have a different number of neutrons. Now, as long as we're on this page, much of what we began to learn about the nucleus and its composition comes from the work of Ernest Rutherford. And Ernest Rutherford is a New Zealander physicist. You don't hear of too many of them, though he did a lot of his work in England, has a couple of Nobel Prizes, and very interesting man, very gentle man and gracious man. From what I've read, I have not been able to find out what his worldview was, what kinds of things he believed. I have an open invitation from Oklahoma State University, and a friend of mine down there who oversees their history of science library, and has invited me to do some research down there sometime, and maybe that's a project for a later date. In any case, one of the things that you ought to recognize is how we write symbols. For example, if we're talking about the different isotopes of carbon, we have carbon 11, carbon 12, carbon 13. Sometimes we write that out the same way we say it. The word carbon and then the number 12 afterwards to refer to a carbon 12 isotope. Notice that the subscript on the bottom left is redundant with the symbol of the element. Carbon is element number 6, and the element number 6 is carbon. What is important is to have the neutron plus proton, the mass number in the upper left the upper left number, 11, 12, 13, that mass number is important to have. You don't have to have the letter Z, the atomic number, in the bottom left. Of course, in the upper right is where you would put what kind of ion it is, if it's an ion, and in the bottom right is where you would put the number of those atoms in a molecule or in a chemical formula. Now you can see here the relative masses of protons, neutrons, and electrons. And you might remember a chart that's in a handout that is in your folder, or it will be soon, and that you also received in both honors chemistry and in AP chemistry, comparing the masses of the proton, neutron, and electron. That if an electron is arbitrarily assigned a mass of 1, the proton would be 1,836 times more massive, and the neutron 1,837 times more massive. In terms of kilograms, you can see that in the left-hand column. And again, the neutron is ever so slightly more massive than the proton. And interestingly enough, it turns out that a neutron is about the mass of a proton plus an electron. And that will be important when we talk about nuclear decay. The charge of a proton and electron are exactly equal in magnitude, but opposite. The neutron has no charge. In terms of atomic mass units, the letter U, you can see that in the middle column. And then what you've never seen before is if we convert this to a unit of energy, mega electron volts. You can see we have 938, 939, and then about a half. And that comes from converting the mass into energy. How do we do that? We use Einstein's equation E equals mc squared, which recognizes that mass is just another form of energy. And if you convert the mass into kilograms, and you can see that in the left-hand column of the chart, and then multiply that mass in kilograms times the speed of light squared, which is about 3 times 10 to the 8th meters per second, you get the amount of energy in joules, which if you convert it into electron volts, which is actually the energy per charge to move a charge through 1 volt, it's millions of electron volts, MeVs, which is a common way in which we talk about the subatomic particles. We talk about them in terms of mega electron volts, and we often convert them into that using a conversion factor of 931 mega electron volts per atomic mass unit. You're going to use that conversion factor in some of your math problems, homework problems. Now, when it comes to finding the size of a nucleus, Rutherford helped us with this by using alpha particles and shooting them at a nucleus and measuring the distance it travels until it begins to feel a substantial force of repulsion. And so, if you look at the equation where it says 1/2 mv squared, what we're doing here is 1/2 mv squared, of course, is the energy, kinetic energy, in joules. And if we take the Coulomb's law of attraction, which F equals K times Q1 times Q2 divided by R squared, and you multiply the left and the right side by R, you get force times R, which is work, in joules, equals K Q1 Q2 over R. So we're basically setting the formula for kinetic energy equal to a variation of the electrostatic force of attraction or repulsion, modified, And we get this equation right here. The number 2 that you see right here, and this thanks to the weird way in which this highlights, I can get rid of that. Just found that out. But that number 2 is because we're talking about the 2 protons in an alpha particle. And the letter Z would represent the protons that are in the large nucleus that we're shooting our alpha particle at. And when we do the math, we can calculate this and find D. The distance that this particle can travel for its closest approach before it's going to be repelled by the nucleus of the larger particle that we're shooting the alpha particle at. And we can simplify that even further and get a very, very rough estimate of the radius of an atom. And we're going to need a very, very small unit of length. And you might remember that 10 to the minus 12th is trillion, 10 to the minus 9th is billion. Well, 10 to the minus 15th is a femtometer, sometimes called a Fermi, named after Enrico Fermi, who we'll come across a little bit later. And so equation 29.1 shows that most nuclei are approximately spherical. We can use that successfully as a model, and has an average radius given by this equation. And let's look in the next page so you can see what those terms mean. Where R sub aught, R with a little o underneath it, is a constant value in femtometers, 1.2 femtometers, and A, remember A is the total number of protons and neutrons, the total number of nucleons. And this suggests that nearly all nuclei, for our intents and purposes, have the same density. And the density of a nucleus is quite phenomenal. If we have a neutron star has a similar density to the density of a nucleus. Of course, those of you that are awake while you're reading this will recognize that a neutron star is a little bit bigger than the nucleus of an atom. Now, moving along. Some nuclei are much more stable than others. But in any case, a nucleus, for the time that it exists, which might be theoretically forever or a fraction of a second if it's not stable, you should understand that a nucleus has got to have some stability to exist at all. And what is holding that nucleus together? And here's the problem that we are trying to answer. How is it that a nucleus made up of multiple protons doesn't self-destruct when all those protons repel each other? How is it that the nucleus can even stay together? And part of the answer is it's got all those neutrons in there that kind of shield one proton from another. But a more comprehensive answer requires us to begin to realize that there is something that we now call the nuclear force. This nuclear force overcomes the repulsive force due to Coulomb's law that would repel the protons. And it enables the protons to stay put in the nucleus. So the nuclear force is stronger than the Coulombic repulsive force. That's also called the electromagnetic force. And when we get to chapter 30, and we've done this before, remember the 4 major forces. The strong nuclear, which is the strongest of all, but it's operates over a very, very narrow, short length of the size of the nucleus. Then you've got Coulomb's electromagnetic force. Then a little bit weaker than that is the weak nuclear force, which is involved in radioactive decay. And then by far, the weakest force of all is gravity, which might surprise you since gravity is what we talked about the most. But the only reason gravity seems like a big force is because the objects that we typically think about, like planets and cars and baseballs and bowling balls, are substantial in their mass and as a result have a magnetic force. But if we were to compare planets and bowling balls and atoms, atomic unit per atomic unit, the strong nuclear force is way, 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 way more stronger than wimpy old gravitational force. Now, there are about 260 stable nuclei. And all of your elements, almost all of your elements, up through element 83, up until element 83, have one or more stable nuclei, on average a little bit more than 3. So you have about 260 stable nuclei. You have about 1,200 or so radioactive or unstable nuclei, for a total number of nuclei of approximately 1,500. Now, if you remember my classroom, and you have a vague recollection of the chart that was behind my chair, a chart that I got because I used it all the time back in Idaho doing research. We studied nuclei all the time, especially charged nuclei. Well, this chart in the back of that you see on this page is a abbreviated, simplified version of the chart that is behind my chair in my room. And this chart, every dot represents a nuclei. And you can see that early on in the chart, down here up through, let's say, element number 20, and this will not let me highlight it, would be element 20 would be calcium, that from hydrogen through calcium, it's kind of linear. The y-axis equals the x-axis. The neutron number equals the proton number. Your slope equals 1. But then as soon as you go beyond calcium, you start needing more and more neutrons per proton to have a stable nucleus. And you can also realize that elements above those black dots in the shaded area represent isotopes that are unstable, and elements in that shaded area below the black dots also represent elements that are unstable. But the black dots represent those 240 or so stable nuclei. That's the line of stability. The dotted line would be a slope of 1, where neutron number equals proton number. Now, once you get to Z equal 83, Z would be beryllium. Lead is 82, beryllium is 83. Once you get there, every isotope of every element from now on is unstable. Now, sometimes that instability, for all intents and purposes, is stable because it's got a half-life in the millions or billions of years. Nevertheless, these are all considered to be unstable with measurable half-lives. Some of them have half-lives that are so short, in the fraction of a second, that they don't last for very long. Now, something that you did not have in first-year chemistry and was touched on in honors in AP chemistry is binding energy. Can we calculate this binding energy that binds the nucleus together, that holds those light-charged protons and neutrons together in the nucleus? And I didn't mention where this nuclear strong force comes from. What is the cause of it? It's one thing to say that neutrons help to shield protons from each other inside a nucleus, but that still is not sufficient, especially when you start getting 40, 50, 60 and more protons in the nucleus. So there's something else going on, and that strong nuclear force is actually the result of some of the mass of the nucleus itself being turned into energy that holds the nucleus together. It's the binding energy. And the way that we calculate this binding energy is we find what is called the nuclear mass defect. Now, when I use the word defect, I don't mean that the nucleus is defective. The defect is the missing mass. Now, in order to get a sense of that, if you look at this part right here, the interesting thing in this equation, this change in mass, delta M, this is the missing mass that must be converted into energy using E equals mc squared. What this missing mass is this. If you add up the mass of the protons plus the mass of the neutrons inside the parentheses there, you get a certain value. Then if you were to find the mass of the nucleus, lo and behold, it's not the same value. It's a little bit less. And that difference in mass is your nuclear mass defect. It's kind of like if we were to add up everybody's mass in the class, we would get a certain value. But imagine our surprise if we were to put everybody in the class then on the same bathroom scale somehow, and we would find out that their mass is different when we have them all together compared to when we add up their independent masses. That's what we mean by the nuclear mass defect. And we measure that nuclear mass defect, in this example, in atomic mass units. We could convert the atomic mass units into kilograms, plug the kilograms into E equals mc squared, and calculate the joules of energy, and then convert the joules into mega electron volts. Or we can leave it in terms of atomic mass units and do the conversion factor of 931.5, and it's a lot faster that way. 931.5 mega electron volts is the energy equivalent of 1 atomic mass unit. So when we are going to be comparing the binding energy, the energy that comes from the nuclear mass defect for different nuclei, obviously it's not a fair comparison if you do, say, heliums to uraniums. So when we find the mega electron volts of the binding energy, we often divide this value by the total number of nucleons to get a fair comparison. The average binding energy per nucleon is about 8 MeVs, 8 mega electron volts. And we need to look at this next graph. This is another very, very famous graph in physics. And what you'll notice there in the shaded area that has iron and nickel in it, around mass number of 60 to 70 or so, that is the area of greatest binding energy per nucleon. So that would be the region of greatest stability. Anything to the left and anything to the right is not quite as stable because it doesn't have quite as much binding energy per nucleon holding the nucleus together. And you can see heliums, or hydrogens I should say, way off to the left, down there at about 1 binding energy per nucleon, 1 MeV. And then it jumps way up to helium, an alpha particle. It drops off a little bit to lithium, number 3, and then it basically has this curve that increases and tapers off around iron, and then it begins to drift downward from germanium all the way down to uranium. Now, there's an awful lot to say about this graph, and we'll say a few things. You can see that in order to become more stable, the elements on the left, if you fuse them together so that their nuclei becomes greater and greater, eventually you can end up with a more stable nucleus like irons, which means that fusion potentially can release energy as you become more stable. By the same token, with uranium, for example, the splitting of nuclei can also cause you to go downwards in terms of the number of particles in your nucleus. and you can become more stable that way. So a graph like this is rather tantalizing because it suggests that fusing smaller nuclei together on the left or splitting larger nuclei on the right improves your stability, meaning when things become more stable, they give off energy. And so we have a lot of energy being given off from the fusion of, say, hydrogen to helium, and not so much energy being given off when you fission or split large nuclei like uranium. In fact, the energy from fusion is about 8 times per nucleon as the energy from uranium per nucleus. Now, energy is not the only thing that results when an unstable nucleus becomes more stable naturally, or when an unstable nucleus through fission or fusion ends up being more stable. Another thing that happens besides the loss of energy, the release of energy, is you get particles given off. Pieces of the nucleus go flying out. And those pieces that go flying out with high kinetic energies, that's radioactivity. It has nothing to do necessarily with radios. And here we go again. Now, we first began learning about radioactivity 100 years ago. And a lot of that work was done by Rutherford. And a lot of that work was done by Marie and Pierre Curie. At the top of the page, you have Rutherford's famous experiment. Put a chunk of radioactive material that they didn't quite know what it was inside a lead container with a hole in it. And as those particles exit the lead container, they enter a magnetic field. In class, I'd ask you, how do you know that's a magnetic field? And hopefully your answer would say it's got all those little green X's. And you should recognize that the green X's mean the magnetic field is going into the page. And so these radioactive particles would exit the box, entering a magnetic field. Now, some particles were unperturbed by the magnetic field. They traveled a straight line to the right before they hit photographic film 100 years ago, and nowadays we'd have a more electronic detector. Those are gamma rays. Those do not get deflected by a magnetic field, which means gamma rays aren't charged. They don't have a positive or negative charge, and for that matter, they're not even particles. They're high-energy photons. But you'll notice the alpha particle. Remember, an alpha particle has 2 protons and 2 neutrons in a nucleus. An alpha particle, if it were to pick up a couple electrons, would be a helium atom. So alpha particles have a positive charge. So get out your right hand. You should be doing it right now. And in your right hand rule, have your hand flat. Put your fingers going straight down into the page. Rotate your wrist so that your thumb is going to the right in the direction that the alpha particle is traveling. And you'll notice that the palm of your hand is facing upward. The palm of your hand is going to push the alpha particle upward. And that's why the alpha particle begins to be deflected and curved upward in its trajectory. Now, let's do the beta particle. And some of you missed this on the last test. The beta particle is a negatively charged particle. So you don't use your right hand. You use your left hand. And when you take your left hand out, put your fingers, go straight into the page. Are you doing that? Put your thumb towards the right in the direction that the beta particle is initially traveling as it exits the lead box. And the palm of your hand is pushing, will be the force pushing the beta particle in a curved path downward. So we have 3 spots that get exposed, or 3 places on the detector that are detecting activity, that are detecting 3 different kinds of radiation: alpha, beta, and gamma. Now, another thing you should notice is that the beta particle is deflected downward way more than the alpha particle is deflected upward. This means that the beta particle must be much, much smaller in mass than the alpha particle. And of course, an electron is much smaller in mass than an alpha particle, which is 2 protons and 2 neutrons. Now, another interesting thing about nuclear physics is we get all of these weird particles, especially when we start smashing things together, and especially when we start picking up particles coming in from outer space that we weren't able to detect 100 years ago. For example, there's a particle that's like an electron, has the same mass as an electron, but it has the opposite charge of an electron. And no, I'm not talking about a proton. Remember, a proton is way more massive than an electron. This particle that has the same mass and has all the properties of an electron, but the opposite charge, is called a positron. And we've never had that before, at least in our formal study. And a positron turns out to be a representative of many, many, many kinds of particles that we call antiparticles. Now, antiparticles are not against particles, antiparticles. An antiparticle is a particle that has all the properties of a regular particle that it corresponds to, but it's opposite in some significant way. In this case, the charge. And we find that all kinds of particles have their antiparticles. And this is talked about in chapter 30, and sadly we will not have very much time to talk about antiparticles at all. Now, Marie and Pierre Curie, if you look at the history box, very famous. Interestingly enough, in the history of nuclear physics, there are a number of women who played very, very prominent roles and also end up having elements named after them, getting Nobel Prizes. And in the area of the physical sciences, women are very much underrepresented. There's all kinds of scholarship money and opportunities available to young ladies who might want to pursue a career in this particular field. And that's true across the board in the physical sciences. In the biological sciences, women are actually represented a little bit more than men are. But in the physical science, they're very much underrepresented. One of my good friends out in Idaho, named Dr. Janie Ingram, not only was she a chemist, but she was in physical chemistry, and she was also Navajo Indian. And so that probably puts her in about the smallest percentage category you can possibly imagine. And she was a very devout Christian, and I count her as a very dear Christian sister in Christ. And it was a lot of fun working with her. And a couple of other people in my group turned out also to be Christians. Very unusual. But she was the minority of minorities. Christian, female, Navajo Indian, PhD in physical chemistry and mass spectrometry. Marie Curie, sadly, in her discoveries in nuclear physics and radioactivity, did not realize until too late that her exposure to radioactivity gave her leukemia. She died of leukemia, I think somewhere in about 34. Her daughter also died of leukemia in 52. Her husband did not die of leukemia. He was run over by a carriage in Paris, France, as I recall, I think in 1904 or 5. So a lot more people still die from car accidents than will ever die probably from nuclear reactors and also from nuclear bombs, at least so far, if you do the numbers. A very important term in physics and in lots of fields of science is the half-life. When we say that something decays, we mean it becomes more stable by shooting out particles. This is very different from biological decay, rotting. Not connected to that at all. And we're not talking about tooth decay either. So if we had time, I would go through a calculus derivation showing how we begin with the assumption that the number of particles that are going to decay is going to be proportional to the number of particles that you have to begin with. So therefore, the rate of decay is proportional to the original particle sample, capital letter N. And we can throw in a proportionality constant, which is negative lambda, because this number is going to get smaller and smaller as the decay takes place. And if we were to go through some algebra 2 and get a graph like at the top of the page and realize that you never know when all of your particles are going to eventually decay and become stable, you can estimate how long it'll take for half your particles to undergo decay. So if you start with n sub aught number of particles, your original sample, you can estimate the time until you get to 1/2 n sub aught. And that amount of time is called your half-life. And then you can do half of a half, which would be 2 half-lives, and half of a half of a half, which would be 3 half-lives, and so forth. And this is a very, very important science concept and an economics concept, because we can talk about the regular halving of things in all kinds of population studies in biology, in all kinds of cancer studies of cells, and also in all kinds of economic studies of quantities of money or quantities of resources. In the end, if you go through the calculus, you end up with equation 29.5, that your half-life equals the natural log of 2 divided by lambda, where lambda is your decay constant and T is your half-life. And so every nucleus that is radioactive, that is unstable, I should say, will have its own unique decay constant and therefore its own unique half-life. And that half-life can be everywhere from a fraction of a second to maybe 3 seconds like with nobelium, or maybe 4.5 billion years like with uranium-238. The point being that a half-life is how long it takes till you get half of your original sample. Remember, 2 half-lives does not equal a whole life. You go half of and half of a half and half of a half of a half. Now, when we go to measure the quantity of these decays per second, there are all kinds of units. And I remember when I was in graduate school for my master's, and this is way back in 1977 when I first started teaching. I was taking a course in nuclear reactor physics, and we were studying this, and you can have all these units, and units, of course, involve conversion factors. And I could do the dimensional analysis. I didn't necessarily know what a becquerel or a sievert or a Gray or a Curie or a Roentgen were, but I could do the math correctly. And the 4 other people in the classroom who were nuclear physicists or PhD nuclear students, they struggled with the math, which was a little bit scary considering 2 of them operated the local nuclear reactor, Sequoia nuclear reactor outside of Chattanooga, Tennessee. In any case, a Curie is 10 times to the 10th power decays. So it's about 3.7 times 10 to the 10th power decays per second is called a Curie. And the becquerel is 1 decay per second, named in honor of Henri Becquerel. And there are other units of radiation used in different contexts or for different parts of the body. Now, example 29.2 shows us how we go about doing this kind of math. And this kind of math begins to get into remembering that what Avogadro's number is, 6.022 times 10 to the 23rd, and what a mole is. We don't need it in this particular equation, but we do it in some of the other math problems. And I'm going to stop there because I've been talking long enough, plus it's time to eat dinner.